Okay, so I'm going to present my work in English because I practiced on English. And I'm going to discuss the structure and mechanical properties of northern Israel's crust and its insights that we have from seismic anisotropy, seismic tomography studies, and numerical simulations. Just a second. Yeah. So strike-slip fault systems are responsible to some of the most devastating earthquakes in history. Understanding their tectonic setting is critical in order to study their geological development and the risk they pose to nearby population. Properties such as the stress field that operates on these fault systems, the secondary structures that develop along their path, and you can see here just how many there are, and the way the various fault segments interact with each other within these systems affect both earthquake nucleation and rupture dynamics, and how ground motion is intensified in their vicinity.
Just 1 minute. Eyal, can you help me here? לא רואים. תמשיך.
Excuse me, please.
Yeah, so northern Israel hosts a relatively complex tectonic setting. The area contains within it two different fault systems, the Carmel Gilboa Faraya fault system, which is an intraplate system within the Sinai subplate, and the Dead Sea fault system, which is a strike-slip plate boundary. The area also hosts a variety of tectonic-related structures, such as basins that are contained, sedimentary basins that are contained within the fault system, and a significant restraining bend to its north, which is the Lebanese restraining bend. Besides these, the area also a variety of major earthquakes have occurred in the past 300 years across the Dead Sea fault system, and you can see their locations on this map. This includes also the two recent earthquakes that happened on the East Anatolian fault in Turkey, but they're related to this system. And within northern Israel, there have been two major earthquakes in the past 300 years, the Rom and the Jordan Gorge fault earthquakes. And this is the estimated location and magnitudes of these earthquakes. It's pre-instrumental data. And besides these, the area also hosts a significant seismic activity all across, and these are all the earthquakes that were recorded by the GSI in the past 7 years. And this is despite the Dead Sea fault system being a slow slip plate boundary. So what we wanted to do in this study was, first of all, to examine how the Lebanese restraining bend to north of Israel affects the local stress regime across the Dead Sea fault system. In the second part of this work, we wanted to examine how the crustal structure looks like across northern Israel, and specifically, we want to understand how the subsurface geometry of the main faults in the area look like, and whether there are mechanical contrasts along these faults. And in the third part of this of the discussion of the talk that I'm giving, I'm going to show results of of numerical simulations of wave fields across our tomography model that shows how ground motion shakes during real case earthquakes. This is used to validate our work. So starting with the first part, now the Lebanese restraining band has developed at a turning point of the tectonic plate boundary. This eastward rotation of the plate boundary in the area is likely to cause major changes in the stress field in this region, as has been observed in various restraining band worldwide. Now, most of the knowledge we have on the local stress field in the area, and these are orientation of stress markers, maximum horizontal compression in the area. They come from the analysis and interpretation of a variety of mesoscale stress markers, which include stillites, calcite veins, and a variety of other markers that you geologists know about. And each site like that has been the subject of numerous studies. So we've collected a lot of data that shows all these stress markers. However, most of these stress markers have either formed a long time ago or have poor constraints on their time of formation, and therefore could represent a power stress regime rather than the present day one. In fact, in this entire region, there are only 2 direct in situ stress measurements taken from boreholes on both sides of the Kinneret Basin, which show more or less a north-south alignment of the maximum horizontal compression in the area with a relatively large range of uncertainty. Recent work involving anisotropy of magnetic susceptibility performed by Rani Sachar and his colleagues shows, again, this north-south alignment of the maximum horizontal compression in the area with a large range of uncertainty, which suggests generally a divergent strike slip type of mechanism in this area. However, 40 kilometers to the north, in the Metula Saddle, both AMS measurements and a variety of mesoscale stress markers, including calcite veins dated to be roughly 10,000 years old, point to an east-west alignment of the maximum horizontal compression. Now, this is significant because it suggests that in less than 40 kilometers distance, there's a 90-degree rotation of the stress field in this area. So what we wanted to do in this study was, first of all, to increase our knowledge on the local present-day stress field in the region. We also wanted to examine whether these undated or old stress markers across the region adequately represent the present-day stress field across northern Israel. And we wanted to better understand this 90-degree rotation of the stress field in this region, whether this is a gradual process across the 40 kilometers distance, or is it a site-specific measurement within the Metula Saddle, for example. For this study, we used the local seismicity that was recorded by the stations of the Israeli Seismic Network, the ISN, and we measured a phenomena called seismic anisotropy. Seismic anisotropy refers to the directional dependency of waves, of the velocity of waves within the material. The velocity of a wave that travels through an anisotropic layer varies depending on its path and polarization direction. And this is usually a result of some organization within the material fabric, which can be grain or mineral alignment. And in the case of the upper crust, it is thought to be due to those cracks that are oriented in the direction of the maximum horizontal compression being slightly more open or dilated than those oriented in any other direction. And as a result, a shear wave that travels from beneath and arrives top layer of the crust will split into two components: a fast component oriented parallel to the direction of the maximum horizontal compression, and a slow component perpendicular to it. So if we're able to measure the direction, the polarization of the fast component, we have a first order approximation of the maximum horizontal compression at a site. And this is nice because it also averages the top few kilometers of the crust, which is a major thing. So we performed our measurements using standard seismic anisotropy procedures across the data set that we have, and we used rigorous quality control measurements in order to ensure that our measurements are reliable. And for each station, we then computed the mean fast polarization direction from the data set that we have at this station. And you can see those histograms representing the distribution of fast polarization directions relative to the mean computed at each station. We also compute the standard deviation, and we use the standard deviation as a measure of telling us how reliable our results are at a station. We consider any station with a standard deviation of above 50 degrees as a poor quality estimate and discard them. And you can see the orientation of the mean fast polarization direction on this map, measured at each station of the ISN in northern Israel. And I'm plotting here only the high quality and moderate quality results, which is nice. And when we compare this with our stress marker data across the area, we see a high agreement on a regional basis. So, for example, if we look at this area around the Kinneret Basin, all of our stations in this region show a north-south alignment of the mean fast polarization direction, which also corresponds to the direction of the maximum horizontal compression in the area, indicated from the stress markers in the region, pointing to a divergent strike-slip type of mechanism. And this also agrees with a variety of focal mechanism solutions that were taken in this region that show a normal faulting on north-south striking faults. This means east-west extension and northwest and north-south compression. And from the Corazim cell northward, we see that multiple stations on both sides of the fault system seem to show a rotation of the maximum horizontal compression in this area and mean fast polarization direction, pointing to a northwest-southeast alignment of those measurements. This is true both for the stress markers in the region and our mean fast polarization directions. And further north, the Metula saddle, we see that both our measurements of mean fast polarization directions and the stress markers in this area indeed show an agreement of an east-west alignment of the maximum horizontal compression, suggesting a gradual process of a rotation of the maximum horizontal compression, which we think is associated with the restraining band in this area and the eastward rotation of the tectonic border in this region. So our work was published here in Tectonophysics, and to summarize, our shear wave splitting measurements commonly align with parallel with the direction of maximum horizontal compression across the region. Those shear wave splitting measurements provide a first order approximation of a counterclockwise rotation of the stress field across northern Israel, which we think is likely due to the development of the Lebanese restraining band north of Israel. So in the second part, I'm going to show a work that we did of mapping the crustal structure across northern Israel. And as I mentioned, we were particularly interested in understanding the subsurface geometry of the main faults in the area and whether there are significant mechanical contrasts that follow these faults. So again, we used the local seismicity recorded by the ISN. We used a larger data set now. And this seismicity catalog is determined by measuring P wave and S wave arrivals across the network and using the local regional velocity model. In this case, it's the Gitterman et al. 2005. The hypocenter locations of these earthquakes are estimated across the region. Now, this velocity model, it's a 1D velocity model, and it assumes a horizontally layered crust across northern Israel, which we know is not the case because the crust is highly heterogeneous, with wave velocities varying horizontally as well as vertically. And this is because wave velocities are dependent on the properties of the material itself, which include its composition, its lithology, the fluid content, its temperature, its confining pressure, and a variety of other factors, all of which contribute to the crust being a highly heterogeneous one. Now, this is a synthetic example that shows depth against horizontal offset, and you can see the velocities within this 2D synthetics. So this is a fast velocity anomaly, and this is a slow velocity anomaly, and you can see how the ray paths that follow waves follow change with respect to those velocity bodies within the subsurface. Now, this, of course, introduces inaccuracies when we try to estimate earthquake locations using a 1D velocity model. So what we did is we jointly inverted those P wave and S wave arrivals from a relatively large data set of earthquakes across northern Israel in order to get both a 3D representation of the subsurface crust and an earthquake relocation catalog based on those 3D velocity models. And here you can see all these are direct station to event P wave arrivals that I have. I have those also for S waves, and just to evaluate how well we covered the northern Israel across this area. So these are my results. My inversion outputs P waves and S wave velocities across the area in a 3D representation, and we can slice them in order to understand how the velocities vary in depth or a distance. So these are P wave velocities on the left and S wave velocities on the right, and these are taken for 1 kilometer depth, 5 kilometers depth, and 10 kilometers depth. And in general, my velocity model shows a highly heterogeneous crust, which mainly associates with the main sedimentary basins in the region. So if we look, for example, at 1 kilometer depth, we see we see a significant slow velocity body around the Kinneret Basin, in particular in the southern part of the Kinneret Basin. And we also see relatively slow velocities measured in the Zvulun and Israel Basin. In In addition, we also see a significantly faster wave velocities on the western side of the Kinneret Basin, on the western side of the Dead Sea fault system, relative to the eastern side. And this continues almost all the way through our region until we reach Mount Hermon, where we have faster velocities measured here as well. If we look at 5 kilometers depth, we still see this association with the main sedimentary basins in the area, and we still see some differences between the faster western side and the slower eastern side, only at a smaller scale. And at 10 kilometers depth, we hardly see any relationship with the surface geology. We can also divide those two velocity models to get a VP-VS ratio 3D volume. And VP-VS ratio corresponds with Poisson's ratio, and therefore says something about the accumulated damage within a rock volume. And we generally identify that we have higher velocities around the Kinneret Basin and beneath areas with elevated topography. We can also have vertical slices of our model, and this is an interesting look at it. And before we do that, we first need to introduce the top of the Judea group. This is from the Rosenthal et al. 2015 gravity model. Now, the Judea group is composed mostly of strong limestone and dull stone rocks, and it is widespread across the region. And the only place where it does not exist is at Mount Hermon. Anywhere else, it makes a significant structural marker across the area. And above it is embedded a softer Sinonian formation, which likely makes it a significant reflector of waves within at greater depth. So we use it as a structural marker within our vertical cross sections, and you can see it follows the depth of the Judea group follows this black dashed line. We also plot the projected relocated earthquakes beneath the velocity model. So you can see it's all the black dots over here. And above it, we show the topography and major faults that this vertical cross-section intersects. So here you can see the Chula Western Border Fault, the Chula Diagonal Fault, and the Chula Eastern Border Fault. And this is, I think it's very interesting because almost all of the seismic activity, this is a cross-section that was taken in the Chula Basin, and almost all of the seismic activity that we're able to identify in this area seems to be located directly beneath the Chula Diagonal Fault, with little to no seismic activity and the two border faults of this region, suggesting that most of the slip occurs along the Chula Diagonal Fault in this area. Further south, at the northern part of the Kinneret Basin, we see a number of interesting things. So if we look here, we see a very fast velocity area, suggesting very strong rocks, relative to the eastern side of the Kinneret Basin. And this is interesting because this velocity, the drop of this fast velocity area seems to correspond with a drop of the Judea group within the Kinneret Basin in the region. It also follows the area where our relocated catalogs seem to fall. which suggests a shallow, high angle western border fault that dips towards the east at a 70 degrees angle. If we look on the eastern side of the Kinneret Basin, so we have deep seismic activity that occurs directly beneath the Jordan Valley Fault, and we have little to no seismic activity at intermediate depths. So it's only shallow seismic activity on a western border fault and deep seismic activity on an eastern border fault. And also, we were able to observe significantly high VPVS values in this region. And it reaches 2.4 in this area, and we think that this significantly high ratio indicates the accumulation of significant damage due to the intense seismic activity in this area. Now, this relatively shallow seismic activity tends to produce normal faulting on north-south striking faults. While on the eastern side of the Kinneret Basin, we see that most of our focal mechanisms show sinistral strike slip motions associated with the Dead Sea Fault system. So we think that a negative flower structure that underlays the entire Kinneret Basin could accommodate those normal faulting faults in the western side with deep strike slip faults on the eastern side. And this structure could also accommodate the asymmetry of the Kinneret Basin, which is nice. And further south, if we look at the Kinneret Basin, we see that we have two different seismic concentrations of seismicity that occur directly beneath the Jordan Valley Fault, suggesting that this is a vertical fault segment, as has been assumed by various other researchers. We can also look at a cross-section across the Dead Sea Fault system, and this shows something interesting, because in areas where the top of the Judea group drops to depths of almost 7 kilometers within the basin, we see areas where we measure higher velocities closer to the surface. And we think that this rise of faster velocities closer to the surface is associated with a thinning of the crust in this area that allows deeper material to rise closer to the surface. We also measured P-wave perturbations across our velocity model, and these are perturbations at the average perturbations at the top 5 kilometers of the crust, which suggests that the western side of the Dead Sea Fault system is about 10% faster than the eastern side. This is interesting because it indicates that there's a bimaterial fault interface that exists along the Dead Sea Fault system, which has profound implications on earthquake nucleation and rupture patterns. If we look, so we don't have the fault system. For some reason, you can't see the fault segments in this figure, but you can see the clusters themselves, which is nice. So you have to trust me that this cluster that I'm showing here, the original catalog relative and the relocated catalog. Also, you can see the depth estimates, and there are two significant ways where the relocated catalog improves on the original catalog. So If you look at those clusters that we have of our relocated seismicity, we have more concentrated clusters relative to the clouds that you see in the original catalog. And while you don't see the faults themselves, trust me that when I say that those are concentrated on existing faults, okay? This is true here for the Jordan Valley fault system. It's also true inside the Kinneret Basin. In the Jordan Gorge fault, you can see how this improves relative to this scattering over here. And of course, in the Hula Diagonal Basin. Another significant improvement that we have in our relocated catalog relates to the depth estimates. So we have our depth estimate of the relocations show a nicer spread across the depth axis, while still preserving the shallow seismicity which was expected in this region. Based on our results, we suggested 3 different possible structures of how the various faults that comprise the Dead Sea fault system interact with each other. So there's a partly continuous fault system that we suggested, where the western side of the Kinneret Basin is connected with some linkage fault to the system itself, although we didn't observe any seismicity during the time span of this study. Therefore, we're Thank you. We've also suggested a discontinuous fault system where the western border fault connects to the rest of the system at greater depth, and there's a detached fault system where this western border fault does not connect at all. And this work was published at JGL Solid Earth, and to conclude this work, our tomographic features correlate well with the surface and subsurface geology in the area. The Dead Sea fault system acts as a shallow biomaterial fault surface across most of northern Israel, and earthquake relocations highlight the subsurface geometry of various faults across the region and show how those various segments interact with each other. Now for the third part, we wanted to understand how those local structures that we were able to measure impact wave field patterns across northern Israel and whether we can use them to validate our work. This has obviously this has profound implications because given the low recurrence time between large earthquakes in this region, we have difficulties in assessing the response of northern Israel to major earthquakes in the area. So if we're able to have a highly accurate and validated 3D velocity model across northern Israel, we're able to simulate real scenario case earthquakes and obviously understand better the risk various places have when a major earthquake will occur. So for this study, I examined 2 velocity models. One is the Gitterman et al. 2005 velocity model projected on a 3D space. And the second one is my 3D velocity model. I composed 3D meshes from them and used 18 real earthquakes to numerically simulate wave field patterns across these meshes. And this is a snapshot at 5 seconds from this particular earthquake. And you can see this is an acceleration wave field across the area. Obviously, we can integrated twice to have displacement measurements, and this is what I'm showing here. So you can see the black line shows the observation, which we use as a benchmark for our results. And the orange one is the synthetic waveform from the 3D velocity model that I have. And the blue one is the Gitterman et al. 2005 model. We then take the amplitude spectra, we transform it to the frequency domain, and we then compute a spectral misfit measurement, which is the natural logarithm of the amplitude spectra of the observation relative to the synthetic. Now, this measurement, to say bluntly, when this measurement is positive, it means that our results underestimate the recorded spectra. When this measurement is negative, it means that we're overestimating the spectra itself. We're aiming for this spectral misfit to be as small as possible, around 0. And this is the spectral misfit that we have. The blue one is for the Gitterman, the orange one is for our 3D velocity model. And this is for each of the components. So for the vertical component, the radial component, and the transverse component. And those are the two horizontal components. We can look at the entire data set that we have. We have multiple stations, 60 stations, in fact, and 18 events, and we did it for both models. We have a lot of simulations. And we generally see that our results, the orange ones, show improvement of almost 35% in evaluating the spectral misfit relative to the observations, which is nice. And we can also look at it at a station basis. So here you can see the mean spectral misfit measured at each station for all the 18 earthquakes. So red areas show that we're significantly underestimating the spectra of real earthquakes in these areas. Green is where we're striving to be. And it seems that most of the misfit that we have in the 1D velocity model concentrates around major sedimentary basins in this area. So you can see the Kinarod Basin. And this is for the two horizontal components, suggesting that this is amplification due to surface waves, which is nice. And in our 3D velocity model, we see a significant improvement relative to the 1D velocity model, but we still see some inaccuracies within the major basins in the area, meaning that we need to improve our velocity models within these basins. So I've had some suggestions on how we can improve our velocity models in the region. One is to incorporate additional data sets to use in a joint inversions such as gravity, receiver functions, surface waves, etc. Another one is to incorporate controlled source data where we know exactly the locations of our explosions or sources or whatever, generating them specifically within those basins will help to improve our knowledge on how wave field patterns and the velocities within those basins, using a joint methods, obviously, full waveform inversion tomography. However, we need larger earthquakes to occur in this region in order to be able to produce this. And of course, cross-border scientific collaboration. We're limited working on only on one side of the Dead Sea fault system. If we were able to work with Jordanian scientists, we could accomplish greater things. Yeah, so this is my work. Thank you.
תודה רבה, גיא.
בטח.
שאלות? כן, לואיס. How did you integrate topography, the tomographic model?
That's a nice question. I actually, so I used the narrower, smaller grid at the closer to the surface. Yeah.
Topographic areas.
Yeah, so I used smaller grid, and I discarded those grid points that are above the surface in my estimations.
Okay.
מה שאתה רוצה.
באניסוטרופיה,
כן.
עלויות הסייסמית, סדקים והעתקים, הם יכולים להשפיע על זה, או אינטואיטיבית?
האמת שכן, ממש.
לא ראיתי בסטרס מרקרס.
אני דילגתי על זה.
אז המסקנה שלך בעצם שזה מתאים לאניסוטרופיה של סידור של המינרלים. כי זה שונה
אני ממש מבין למה אתה מתכוון, אבל אני לא חושב שזה קשור למינרלים, או לפחות לא שאני ראיתי, מהסיבה, אולי אני יכול לתקתק את זה פה. רגע. הנה. הסיבה שאני לא חושב שזה קשור למינרלים, אני חושב שזה קשור לסדקים קטנים שמתרחשים קרוב מאוד לפני השטח, זה בגלל שהמדידות שלנו פשוט מתאימות לנתונים של סטרס, כאן לאורך האזור. אנחנו משתמשים, יש לנו מדידות של סטרס שקיימים פה באזור, ואנחנו פשוט מוסיפים על המדידות האלה את האניזוטרופיה שמדדנו.
מדידות של סטרס אתה מתכוון לכיוון הסדקים?
אני מתכוון לכיוון של המאמץ המקסימלי, המאמץ האופקי המקסימלי, כמו שהוא נמדד מסטילוליטים, מהתרחבות של ורידי קלצית וכו' וכו'. כיוונים של פולט.
עוד שאלות? כן,
זו שאלה מתאמרת אולי, עד בהקשר הזה בדיוק, איך אתה מפרד רעד הספוק העליון, וגם גם באירופיה ופתחה, זה אנחנו יודעים לגבי העומק. שאלה שנייה, ואם אתה יכול בעקבות האנליזות שלך להציע איזשהו מיקום שאפשר לשים מערך ארעי לאיזשהו שנה או משהו כזה, ולצבור עוד נתונים בשביל לחדד איזה משהו שנראה לך שקיים, הרזולוציה של העבודה שלך לא מספיקה שהיא הרגעת שם,
יש כמה. אז קודם כל, בנוגע לשאלה הראשונה, אני אולי שכחתי לציין את זה, סליחה, אלה רעידות, אנחנו מודדים את זה מרעידות קרום, רדודות יחסית, כן? כלומר, זה באמת נכון שאם היינו משתמשים, אתה יודע, בנתונים נגיד מהצד השני של כדור הארץ, שעבר דרך המעטפת, של גלים שעברו דרך המעטפת, אם היינו משתמשים בתכולת תדרים מסוימת, היינו יכולים לראות דברים מעניינים שקשורים במעטפת. אבל אלה רעידות יחסית רדודות שקרו בקרום, שהתרחשו בקרום, בסביבה שלנו, אז זה נתונים ממש מהחלקים העליונים של פני השטח, מה גם שהסדקים הללו, ככל שאתה נכנס יותר עמוק, אז יש לך confining pressure מכל הכיוונים, ואז הסדקים האלה נסגרים, אז בעצם אנחנו כבר לא רואים איזה משהו משמעותי. אני חושב שכן היה מעניין אותי, אני לא נכנסתי לזה יותר מדי לעומק, כן, אבל נגיד נסתכל פה על המדידה בנווה עתיב, כן, שגם מתאימה להערכות על כיוון המאמצים באזור הזה. אז סדרה של מאמרים שחכמים ממני עשו, מראה שיש חלוקה של מאמצים ושל מאבטים לאורך בלוקים, אז בלוקים מסוימים לוקחים מאמץ לכיוון צפון דרום, ובלוקים אחרים לוקחים מאמץ לכיוון מזרח מערב. אני חושב שהיה מאוד מעניין אותי נגיד להסתכל, לבנות איזשהו מערך לאורך כל הקטע הזה, ולראות באמת מה קורה שם.
שאלה אחרונה, שוב.
אפשר בזום?
כן. מה קורה, צחי?
טוב, מה נשמע? הרצאה
בסדר.
מצוינת. יש לי שתי שאלות, אני לא יודע כמה אתם בלחץ זמן, אני אתחיל מהגדולה יותר. אתה הראת את ההפרשי... שומעים אותי?
אני שומע.
אחלה. אז הראת את ההפרשי מהירויות בין הצד המזרחי והמערבי, הפרשים בעומק של 5 קילומטר. אבל
נכון.
רוב הרעידות מתחילות בעומק עמוק יותר. אני לא יודע אם רוב, אבל הרבה רעידות מתחילות בעומק עמוק יותר. אתה יודע איך זה נראה בעומק עמוק יותר, ואם יש לזה השפעה לדעתך על כיווניות של רעידות בהעתק?
תחזור על השאלה.
אז אתה שואל לגבי רגע, אני אחזור על השאלה, כי זו שאלה ארוכה. נעשה חיימאגו. אז אתה מדבר על ההבדלי מהירויות בין הצד המזרחי לצד המערבי, ואתה אומר שאנחנו הצגנו משהו שהוא קשור, שהוא נמצא בעיקר בחלק הרדוד של הקרום, אבל רוב הרעידות קורות בחלקים יותר עמוקים. ומה ההמשך של השאלה?
אם אתה יודע איך זה נראה בעומק עמוק יותר, ואם יש לזה השפעה על כיווניות של רעידות עתידיות לדעתך.
אז אתה שואל איך זה נראה יותר עמוק, ואם יש לזה השפעה על כיווניות של רעידות בעתיד. אוקיי, אז קודם כל זה מאוד מעניין מה שאמרת. באמת, ספציפית באזור הזה, אני לא יודע לומר אם רוב הרעידות הן עמוקות יותר, כן? כלומר, אתה יכול לראות שהרבה מאוד מהרעידות שאנחנו... סליחה, אבל תגיע אותי שזה כזה איטי. טוב, אז בואו נשאר פה נגיד. הרבה מהרעידות שמדדנו פה באזור, למשל באזור של הכנרת, זה רעידות יחסית רדודות, כן? רוב הרעידות מתרחשות שם בעומק של עד 5 קילומטר. אני חושב שהייתי מעדיף באמת לעבוד עם רעידות עמוקות יותר, או אתה יודע, זה היה יכול לדגום חלקים יותר מעניינים, אבל פשוט אין הרבה כאלה באזור. באמת, ניסינו לבדוק עד לאיזה עומק זה מגיע, ההבדלי מהירויות האלה בין הצד המזרחי לצד המערבי. אנחנו חושבים, בעומק של 8 קילומטרים אתה כבר כמעט לא רואה את זה. אתה יכול להסתכל אפילו, אתה יכול להסתכל אפילו פה, בתוך הדוגמה הזאת, כן? 10 קילומטרים, כבר אין באמת הבדל בין הצד המזרחי לצד המערבי של הטרנספורם. קראתי הרבה מאמרים שמראים שאתה יודע, הרעידות הגדולות בתיקי סטרייק סליפ כאלה, יש להם נטייה גם לקרוע את פני השטח, כן? אני מתאר לעצמי שיש לזה השפעה משמעותית על כיווניות של העתקים, אבל אני לא יודע לומר.
תודה,
כן.
אנחנו נסתכל בזה, תודה רבה.
תודה.
תודה רבה, גיא. מצוין, כל הכבוד.